Okay, yeah. So let's say we have a polynomial of this format. You already know how does a polynomial look like. If you don't know, don't worry. You can actually get the basic right now. Dot, dot, dot. It will go up to x to the 0. Okay, where of course your an can't be 0. Okay. Okay. Now we want to see how does this graph, or rather the graph of this polynomial, look like, or how does it behave? How can you relate this to one of the formats which you already know? Okay, that's quite interesting, to be the least. Okay, now what if I say that this graph actually looks like the graph of, let's say, y equals an x to the n. What if I say that the graph of this huge polynomial, or this big function, actually looks like this? Soon you'll see that this is actually true. And for that, of course, we'll take one example and see how can you relate that to any of the formats or any of the graphs we already know. Okay. Okay. So let's take one example. Example 1. And of course, you have it in the PD or in the PPTX file for 4.1. If you want, you can always open that and see the example I'm working on. And as I said, if I take examples from anywhere else, I'll let you guys know. But if I don't say anything, that means I'm taking the example from the resource. Okay. So let's take this polynomial x to the 5 plus ax cubed plus bx squared minus 2x plus 3. Okay. So this is a polynomial, and we want to see how does this graph look like. Okay. So first of all, a +1 question for quiz 3, which will be next week. I'll discuss about it before we finish. So get ready for the +1 question. How many turning points will be there for this particular polynomial? In the graph, of course, how many turning points will be there? Ryan got it right, exactly. 4, because we know that if our highest exponent, or the degree, is n, then we'll have n minus 1 turning points, right? So that means for this guy, we have 5 as the degree. The exponent is, the highest exponent rather, is 5. So we'll have 5 minus 1, or 4 turning points. Yeah, that's a good point. That's a good quick answer. Okay. Excuse me. Okay, now let's go and find some different properties of it and see what happens. We'll have 4 what? Turning points. That means in easier English, the turning point is where your graph actually changes its direction. That means if it was going upwards, it will now start going downwards, or the vice versa. That's a turning point. Okay. Okay. So let's start. Let's start with the y-intercept. Okay, so if we plug in, or let's start with plugging in x equals 0, that will be our y-intercept, right? Because if you remember, we said that if we plug in 0 in place of x, whatever we get in return will be our y-intercept. Okay, so if we plug in 0 in place of x, as far as we can see, all this will become 0 because x is 0. So we'll be left with this guy. So that means our y-intercept is this. Okay. Okay. Now, if we want to get the x-intercept, let me write it for you. So the y-intercept is 0, 3. Now, next up, we want to find the x-intercept. And for the x-intercept, we'll actually put 0 for this. So that means now f of x will be 0, right? And if we solve it for x, we'll get the x-intercept. Okay, let's try that. So x to the 5 plus a x cubed plus bx squared minus 2x plus 3. And for our convenience, we'll consider a and b's are greater than 0. So what we'll do, we'll actually remove this, okay? Or consider that that's not here. So let's say we can actually write this just to find the x-intercept easily, okay? We can actually keep those, but just for convenience, we can do that. Although, let me give you a quick hint. Although you don't need to do this all the time, okay? You don't need to do this all the time. You can actually see the equation or the function and decide how does this graph look like, okay? We can actually do that. Okay, so first of all, if we solve it for x, how many solutions will be there? You have seen that in Math 95 or Math 96. Anyone? If you don't remember, no worries. I'll let you guys know, but you can give it a try. If you have an equation like this, okay, if you solve it, yeah, how many solutions for x there will be? How many values of x there will be if you solve it for x? Okay, Ryan said 5. Why do you think it's 5? The exponent is 5. Yeah, exactly. So if you remember from Math 95, once again, if you don't remember, don't worry. We'll actually try to cover and make you guys remember all those things as far as the properties comes in front. We'll actually go back and try to remember those. So if you have an equation, the highest exponent gives you an idea how many solutions there will be, okay? So if you have x to the 5, in general, you will actually get 5 values for x, okay? 1, 2, 3, 4, 5. You will actually have 5 values for x. It could be identical as well. It doesn't mean that you'll have 5 distinct solution for x. It could be identical. Some of those could be identical. but by x to the fifth, we get the idea that if we solve it, we'll have 5 different solutions. Okay, so now, as you can see, it's quite difficult to solve it, right? It's quite difficult to solve. But as we know a couple of other things, we can actually decide that how does this graph will actually look like when A and B is greater than 0. So let's, okay, so if it was x to the 10, there would be 10 values of x. Yeah, of course. If it's x to the 10, if you try the solver, you can try, I guess, Wolfram Alpha. That's a free platform where you can solve this type of equations. You can try MATLAB. That's a different thing though. But if you try online, you'll see a couple of different platforms where you can solve this. So yeah. The highest exponent gives us the number of solutions there will be. Again, those may be, one or two of those may be identical, could be distinct, doesn't matter, but it means that it will have 10 solutions in general. Okay, so fortunately, if you take a look at the informations we have, it intersects y-axis in just one place, okay? And we know that it has, how many turning points? 4. It has 4 turning points, okay? And also, we know that this graph will resemble somewhat of x to the 5, okay? It will not exactly be the, it will not exactly look like x to the 5, whatever the graph of x to the 5 is, but definitely it will behave like that, okay? This graph will definitely behave like that. So clearly, we can, if we have a graph of x to the 5th, we can actually come to the conclusion that whatever your graph, this will actually be given. I'll soon show you one example of it. This graph will be given. So once you know this, that this looks like x to the 5th, okay, and you know it intersects at this point, and you know it has 4 turning points, you'll be actually able to identify which graph actually is this. So what does this mean? That you will be given a couple of graphs, let's say 4 choices, and from that you need to identify which option actually gives you the graph of the polynomial by just identifying or knowing these informations. Okay, now let me quickly show you the graphs, possible graphs of this, and then you will be actually able to find it. Okay, so let me draw a bunch of graphs for you, or if you have it in front of you, you can always see that. So this is one of the graphs. Let's say that's our option A. Okay. Option B. That's it, option B. Option C is, wait, are we not looking for x-intercepts? Well, you can solve it as I said. You can always solve it and find your x-intercepts. But as you can see, we have 5 different, we assume that there will be 5 solutions. It could be identical as well, but as we assume that there will be 5 solutions, it will be quite time consuming, okay, which we don't really want. But again, you can always try the solver If you want, I can show that as well. I don't mind showing that. I can show that as well. You can try the solver and okay, are we just going to have to pick up the graph out of 4 instead of graphing it ourselves? Yeah. Okay, so the first thing is I won't give this question in your tests or homeworks. As far as I have seen or I have set up the question, I won't give you this question that, hey, you need to graph this polynomial. This will be too much for you guys. I don't, want to put so much pressure on you guys. But what I want you to do is to understand how you can actually eyeball the problem, and ideally you can see how the graph look like, how this actually behave, this function actually behave. I want you guys to know, you don't, I don't think you will face this in any of your assignments or tests and etc. Okay, but that doesn't mean that you don't need to learn this. I want you guys to learn this. This is not difficult. As you can see, we already know that how to find the number of turning points. We know that how to calculate y-intercept. We also know, although it will be time consuming more or less, but we also know how to calculate the x-intercepts and all that. So if we know the basic graphs and all, for a couple of core functions, we'll be able to eyeball the graph, or we will be able to understand how this graph behave. I just want you guys to learn this. I really hope you will not face this on the test. By chance, if I give it, you can always give me a reminder that, hey, you said we won't face this in exams, despite the fact you have put this in the exam, and I'll give you full credit on that. Just in case if I give that, okay? So don't worry. Okay, so number C will be okay, and number D will be like this. Oops, sorry. Okay, now by just eyeballing, who can tell me which one this graph, or rather which graph actually gives you uh, uh, the resemblance of this function? Okay, so I have one answer. It looks like C. If you can't see the graph, let me show you the graph real slow. Okay. Okay, so I have two answers of C. Anyone else? Daniel said B. Again, don't look at the answer on the PPTX file. Try yourself. Again, what I always try when, well, I'm a student as well, but whenever I'm teaching, what I really want you guys to do is to try first without watching the solution. Try first yourself, then check and see whether your work is done. If it's okay, then try one more to see that whether your concept is completely right or not. If you're wrong, then try and check where did you get this wrong, etc., etc. Okay, this way you can learn better. Anyway, so I have two different answers, two C's and three B's. Okay, yeah, okay, so yeah, I get the point. Yeah, so excuse me. So as Pearson said, he has a valid point. He said he chose C. Let me quickly see C. Okay, he chose C because he can see 5 intercepts for X, right? So he chose C. Okay, I guess Chris has his own reason as well. So that's quite a valid reason again. But if we see the information we have, let me write it for you. So we have 4 turning points. The y-intercept is at 0, 3. And what else we have? Is there anything else? No, so far these are the two. Oh, this will behave like y equals x to the 5. So these are the three informations we have. Plus, in addition to that, we know that we have x-intercepts, which gives us 5 points, but we still don't know whether any of these 5 is identical to the other. So that means, as Pearson said, this has 5 intercepts. This clearly says that we have 5 distinct x-intercept, right? But we still don't really know that. Okay, so what we already know, let's try on this. We have 4 turning points. The y-intercept is at 0, 3, and it behaves like y equals x to the 5. So for now, let's say you don't really know how does this graph look like, just for example, just for now. But we know that how does this look like. Okay, we have 4 turning points, and the graph goes through the point 0, 3. So first of all, let's try and see option A. It definitely is not 0, 3, right? It's definitely in the negative direction for y. So this is not the graph. One less. Let's try option B. Yeah, it does look like it has intersected the y-axis at somewhere 0, 3, right? It looks like that. Let's see the next point. We have 4 turning points. Let's see how many turning points are there. 1 is here, 1 is here, third one is here, fourth one is here. Yeah, looks like this could be, I'm not still saying that this is the answer. This could be our answer, okay? Can you see how I'm doing this? That's the actual way. Is there anyone who is still confused what we're doing here? We can actually rediscuss it, because this is really a core concept. It's not difficult, but it has some places where you can make a mess, okay? Okay, next. It also looks like that it has intersected the y-axis at somewhere 0, 3. Okay, but let's see how many turning points it does have. 1, 2, 3, 4, 5, 6, 7, 8. So that means this is not our graph. Okay, we can actually go for the next one, because this doesn't satisfy one of the properties we have. Okay, we can eliminate this from our possible answers. Okay, let's go this. This one also looks like it intersects at 0, 3. Let's see how many turning points we have. 1, 2, 3, 4. Okay, so this one also has a possibility for our answer. So we have 2 different answers now, B and D. Okay, now from this we can only see one one difference rather, not differences, sorry. So we can only see one difference between this graph of B and D. This one starts from here and it goes to the positive infinity. That means it's actually on the increase. Can you see that? Whereas this one, just the opposite. It starts like this and it ends like this as well. That means for B, it was increasing at the end and at the boundary points rather. And for D, it's decreasing at the boundary points, okay? So now this information of y equals x to the 5 will come handy. It's because A and B are greater than 0 on graph B. For positive A's and B's, it can still behave like this, okay? It can still behave like this. Yeah, that's a good point though. A's and B's are positive. So that means that might give you an idea that the graph will be positive everywhere, but that's not the case. Even though A's and B's are positive, it can still be negative. The functional value can still be negative. Okay, so how does this graph y equals x to the 5 look like? If you somehow know that, then the rest is done and dusted. So the graph of y equals x to the 5 looks like this. Okay, looks like, it doesn't look like exactly it doesn't look exactly like this, but what I mean is that it's actually on the increase. Okay, or if you go this way, go to your backward, it's actually decreasing slowly and slowly, unlike this. So again, if you know how does this graph look like, then we can eliminate this as well, and then we can say that, yeah, finally this is our answer. That's why I'm repeating myself. If you remember, I said that it's really important so to remember how does some core graphs look like. You know, it will actually save you a lot of time. Why are we eliminating D? Well, as we said, the graph of this polynomial actually behaves like y equals x to the 5, and y equals x to the 5 actually looks like this. It quite similar to this. That's why we eliminated this. Okay, that means if you go to your left, it will slowly and slowly be decreasing. Okay, like this. Whereas for D, as I am going to my left, it's actually increasing, as you can see. Okay, so that's one way to identify how does our graph look like. Okay, so again, it's really important, first of all, to know how does this graph look like. And I've said this over and over again, that it's really important. I would say that you need to know the graph of x to the 5th, but it's really important to at least know these two graphs, to know this graph. What else? Y equals x. At least to know some of these graphs. You know, it's really important. This actually helps you a lot. This gives you an idea what's going on. Let's just say that you can't remember how does this graph y equals x to the 5 looks like. Okay, now again, your concept comes really handy. You know that this is an odd power, right? This is an odd power. So you will have these points on the graph. Okay, because negative will always give you something negative, positive will give you positive, 0 will give you 0. You know, for odd positive number, for as an exponent, we have these points in the graph. So this will definitely go through these 3 points. Okay, at least I know that. So that means it's actually on the decrease. It's actually decreasing. As you are moving to your left, the graph is actually decreasing. And that actually should be enough to see that, yeah, as I'm moving to my left, this graph is definitely decreasing, right? This function is going on. As I'm moving to my left, by the way, I'm not talking about this direction. Don't get confused by that. As I'm moving to my left, slowly and slowly, you can see this graph is going down. So definitely, this is what we're looking for. Excuse me. Okay, so any question from this? No, for even, it's actually, you got it almost right. It's actually -1, 1, 0, 0, and 1, 1 for any positive exponent any even positive exponent, you will have these points on the graph. So again, it's really important to know these stuffs. So it's a parabola? No, it's not a parabola. So a parabola is of this shape. It could be like this as well. Okay, it could be any of this format, but what I mean, it will look like this. It could be the mirror image of it. It could be shifted sidewards, sidewise, but it will look like an open bowl, a parabola. That's not a parabola. That's something different. Okay. Okay. Now, any other question from this? Otherwise, we'll move to 4.2 and graph one more polynomial. Previously, we have seen example 1. Now we'll try example 2 and see how can we graph it. Okay. Any other question from this? Okay, looks like no question. So just give me a second. Let me stop recording now.